Imagine that you have a box containing n identical fermions with total energy E. Each particle is in a particular state, and since the particles are fermions, there can be at most one particle per state. There are G sub I states with energy E sub I, and there are N sub I particles with energy E sub I, and we denote the fraction of states with energy E sub I that are occupied by particles as F sub I. The total energy can be written as the sum over E sub I N sub I, and the total number of particles can be written as the sum over N sub I. An example is shown on the bottom of the screen. States are represented by a yellow dash, and fermions that occupy states are drawn as a red dot. Here we see a system that has 5 fermions, so capital N equals 5. There are 4 energy levels with energies E sub 1, E sub 2, E sub 3, and E sub 4. The energy levels are drawn so that energy increases from bottom to top. There are 4 states with energy E sub 1, so G sub 1 equals 4. There are 2 particles with energy E sub 1, so N sub 1 equals 2. Half the states with energy E sub 1 are occupied, so F sub 1 equals 1/2. Similarly, you can find G sub 2, G sub 3, G sub 4, N sub 2, N sub 3, N sub 4, and F sub 2, F sub 3, and F sub 4. F sub I is called the fermi dirac distribution, and we would like to derive it for a system of fermions at temperature T. To proceed, we need to introduce the concept of a microstate and the configuration. Consider a system with states as shown on the screen. There are 2 states with energy 0 units, 2 states with energy 1 unit, and 3 states with energy 2 units. Imagine that we have 2 particles with total energy 2 units. There are 7 distinguishable ways to fill the states with fermions, subject to the constraint that the total energy is 2 units and there are 2 particles. We call each way to fill the states a microstate, so there are 7 microstates for a system of 2 particles and 2 units of energy for this particular system. Each microstate has a different set of N sub I, that is, a different list of numbers, N sub 1, N sub 2, and N sub 3, such that there are N sub 1 particles in level 1, N sub 2 particles in level 2, and N sub 3 particles in level 3. We can divide the microstates into different configurations, such that 2 microstates with the same N sub I are in the same configuration. In our example, there are 2 possible configurations. Configuration A has 1 particle in level 1, 0 particles in level 2, and 1 particle in level 3. Configuration B has 0 particles in level 1, 2 particles in level 2, and 0 particles in level 3. We say the weight W of configuration A is 6 because there are 6 microstates with configuration A. Similarly, the weight of configuration B is 1 because there is 1 microstate with configuration B. Each energy level I also has a weight W sub I, which is the number of ways to place N sub I particles in G sub I states. For example, in level 3 of configuration A, there are 3 ways to place 1 particle in 3 states, so W sub 3 equals 3. For level 1, there are 2 ways to place 1 particle in 2 states, so W sub 1 equals 2. For level 2, there is 1 way to place 0 particles in 2 states, so W sub 2 equals 1. Notice that the total weight of the configuration is the product of the weights of the individual levels. Now we need to derive a general expression for the W sub I in terms of the N sub I and G sub I. We proceed with an example. Suppose we are trying to fill 3 states with 2 particles. Color 1 particle green and the other red. There are 3 ways to place the green particle. For each of those 3 ways, there are 2 ways to place the red particle. So, there are 6 ways to place both particles. However, fermions are identical particles, so microstates that look the same, if you color all dots orange, are the same microstate. There are thus only 3 distinct microstates. More systematically, the way we got W sub I equals 3 is as follows. There are 3 ways to place the first particle and 2 ways to place the second particle. However, any permutation of the particles yields the same microstate, because fermions are identical. and there are two permutations of the two fermions, so we have to divide by 2 because we overcounted by a factor of 2. In general, there are g sub I ways to place the first particle, g sub I minus 1 ways to place the second particle, g sub I minus 2 ways to place the third particle, etc., until there are g sub I minus n sub I plus 1 ways to place the n sub I particle. But any of the n sub I factorial permutations of these microstates are the same microstate because we are dealing with identical particles. Multiply and divide by g sub I minus n sub I times ... times 1. Use the definition of g sub I factorial and g sub I minus n sub I factorial. This is the general formula for the number of ways to fill g sub I states with n sub I fermions. To get the number of microstates corresponding to an entire configuration, multiply the W sub I together for each level I. Because there are W sub 1 ways to fill level 1, and for each of those ways there are W sub 2 ways to fill level 2, etc. We assume that the system will be found in the configuration with the largest number of microstates. This is because we assume that all microstates are equally likely. So if the system is randomly changing microstates, it will, just by chance, be found in the configuration with the most microstates. If we can find the n sub I that corresponds to this configuration, the fermi dirac distribution is simply the number of particles with energy E sub I divided by the number of states with energy E sub I. We know that the differential of W is 0 when the independent variables n sub I are such that W is maximum. However, because the expression for W involves factorials, it is more convenient to set the differential of the natural log of W equal to 0. This occurs at the same values of n sub I, as can be seen by noting that the differential of the natural log of W is dW over W, so that we can multiply d natural log of W equals 0 by W to get dW equals 0. Now let's find the differential of the natural log of W. By definition, the differential of a function is the sum over the derivatives of the function with respect to the independent variables times the differential in the independent variables. W is the product of W sub j's. The natural log of a product of factors is the sum of the natural log of the factors. Replace W sub j with the expression we just derived for W sub j. Use the product rule of logs. Use Stirling's approximation to replace terms of the form natural log of x factorial with x times the natural log of x minus x. Cancel the n sub j minus n sub j and g sub j minus g sub j terms. Bring the derivative operator into the sum. G sub j is a constant because the number of states with energy E sub j can't change. So the derivative of G sub j with respect to n sub I is 0. Use the product rule on the other terms. Then use the chain rule on the terms with the logs. Cancel the factors that are the same on the top and the bottom. Cancel the plus derivative of n sub j with respect to n sub I minus the derivative of n sub j with respect to n sub I. Since the n sub I are independent variables, the derivative of n sub j with respect to n sub I equals 1 if j equals I, and 0 otherwise. Thus, the derivative of n sub j with respect to n sub I equals the Kronecker delta, delta sub ij. Factor out delta sub ij. Combine the natural log terms. When a sum over j contains a factor delta sub ij, we can actually perform the sum by simply replacing the index j with I and getting rid of the summation sign. Now remember that we have two constraints. The total number of particles is constant, so dn equals 0, and n can be written as a sum over n sub I. We can multiply both sides of dn equals 0 by an arbitrary number alpha. Similarly, the total energy is constant. We can write the total energy as the sum over n sub I E sub I, and thus the differential of energy is the sum over n sub I d sub I plus the sum over E sub I dn sub I. We are keeping the volume of the box constant, so the energies of each level don't change. Multiply both sides of dE equals 0 by an arbitrary number beta. So we have three equations that describe the configuration with maximum weight W. First, the differential of the natural log of W is 0. Second, alpha times dN equals 0. And third, beta times dE equals 0. We can add these three equations to get a single equation that describes the configuration of maximum W with particle number and total energy conserved. Replace natural log of W in this expression with its expression derived previously. Combine the summation terms. Since we have included all of the constraints, the dN sub I terms can be varied arbitrarily. Therefore, the only way the left-hand side of it can be 0 is if all of the coefficients of the dN sub i's are 0. Thus, set the coefficients equal to 0. Subtract alpha minus beta E sub I from both sides. Take the exponential of both sides. Multiply both sides by n sub I. Add n sub I to both sides. Factor out an n sub I. Divide both sides by e to the negative alpha minus beta E sub I plus 1. By definition, the fermi dirac distribution is n sub I over g sub I. So f sub I equals 1 over e to the negative alpha minus beta E sub I plus 1, which we can rewrite as e to the negative alpha over beta minus E sub I times beta plus 1. To find alpha and beta, we note that the extremization equation can be solved for dE by subtracting d natural log omega and alpha dN and dividing by beta. But the fundamental equation of thermodynamics states that dE equals T ds minus P dV plus mu dN, where E is the internal energy, T is the temperature, S is the entropy, P is the pressure, V is the volume, mu is the chemical potential, and N is the total particle number. We are holding the pressure constant, so we can set dV equals 0, and the fundamental equation of thermodynamics becomes dE equals Tds plus mu dN. We have two expressions for dE, so to ensure that they are equal, we must set corresponding terms equal. Setting the first terms equal shows us that S equals K, natural log of W, and beta equals negative 1 over KT, where we have inserted a Boltzmann's constant, K, simply to make sure that entropy has units of entropy. Setting the second terms equal shows that negative alpha over beta equals mu. We can replace beta with negative 1 over KT and negative alpha over beta with mu in the expression for f sub I, giving the final expression for the fermi Dirac distribution.